Welcome back to Linear Circuits. I'm Dr. Harris. The topic of this lesson is resistance and Ohm's law. And by the end of this lesson, you should understand the resistance property of materials, as well as the relationship between resistance, current, and voltage. This lesson also builds upon electric current, which is the quantity of charge that passes through a given area in a specified time, and voltage, which is the energy either gained or lost per coulomb of charge. So, what exactly is resistance and resistivity? I've shown here a cartoon of, we can say, any material, perhaps a copper wire. When charged particles flow through that material, they encounter an electrical resistance. And the electrical resistance is determined by the material's cross-sectional area A, its length L, and its resistivity ρ. Now specifically, resistance R is the product of ρ and L divided by the cross-sectional area A. The resistivity is an intrinsic property that quantifies the material's opposition to charge flow. And just for reference, the resistivity of metals, which are excellent conductors or have very low resistance, the resistivity values range from 10 to the minus 8 to 10 to the minus 3 ohm meters. But if you consider rubbers, which are not good conductors of electricity, they have high resistivity or high opposition to charge flow. Their resistivity ranges from about 10 to the 5 to 10 to the 15 ohm meters. The variable that we'll use for resistance is R, and the unit will be volt amps or ohms. Now, conductance and conductivity have an inverse relationship to resistance and resistivity. Electrical conductance measures how a material allows charge to flow. And the conductance G is the reciprocal of the resistance, or 1 over R. You could also write it as sigma A over L. So now we have another term where we used resistivity for ρ. We use ρ for resistivity. Now we're using sigma for conductivity. It's also an intrinsic property that quantifies a material's receptiveness to charge flow. In other words, conductivity is the reciprocal of resistivity. Materials that have a high conductivity will have a low resistivity and vice versa. For conductivity, we'll use the variable G, and the unit is amps per volt or Siemens, or an upside down omega, which we call moles. So given this information, let's take a short quiz and calculate the resistance and conductance of a material. Pause the video and take this quiz where you find first the resistance of a copper wire and then the resistance if the area doubles. After you work the problem, press play and we'll solve the problem together. So let's consider a 1 meter long copper wire has an area of 0.001 square meters. The copper's resistivity is 2 times 10 to the minus 8 ohm meters. Find the resistance of the wire. We know that R is ρ L over A, and our resistivity is given as 2 times 10 to the minus 8. Our length is 1 meter, and our cross-sectional area is 10 to the minus 3. So that gives us a resistance of 2 times 10 to the minus 5 ohms. Now the second question asks, if the wire's area doubles, how do the resistivity and the conductivity change? So if we call R2 as ρ L over 2A, then that's the same as 1/2 the resistance of R1, or 10 to the minus 5 amps. So by doubling the cross-sectional area, we cut the resistance in half. Or conversely, we know that G is 1 over R2, or 1 over 10 to the minus 5, or 10 to the 5. So our conductivity is also going to double. Our resistance goes down by half, but our conductivity doubles. So now we see resistance and resistivity versus conductance and conductivity. We have charged particles that flow through this material to encounter an electrical resistance, and a voltage is produced by that current flow that's proportional to the resistance of that material. That proportionality relationship is Ohm's law, which is V equals IR. The voltage is the current times the resistance. So if we have two electrical devices, one with a current I1 flowing from plus to minus V1, then we have V1 equals plus I1R. If you consider the other device, V2, where we have current flowing from minus to plus, V2 equals minus I2R. So the same mnemonic device that we've used all along, whichever sign for the voltage you get to first, you can use that one in your calculation. For V1, the current gets to the plus sign first, so it's a positive current. When calculating V2, the current gets to the minus sign first, so we use a minus current. Now apply Ohm's law in the next quiz. Again, pause the video, find I1, find V2. After you've done that, we'll go back and solve the problems together. Let's solve for I1. Since the current gets to the plus first, in this case, V equals plus IR. We're solving for I, so I is V over R. Our voltage is negative 6 volts. Resistance is 2 kiloohms, so our current is a negative 3 milliamps. For V2, now our current comes to the minus side first, so V equals minus IR. That's V2. Here, it's V1. And that's I1. So V2, which is minus I2R, is a minus 6 milliamps times a resistance of 4 kiloohms. V2 is a negative 24 volts. The key concepts covered in this lesson are first, that electrical resistance and conductance are determined by a material's cross-sectional area, its length, and resistivity or conductivity. So R is rho L over A, or G is sigma A over L. Also, Ohm's law states that the voltage is the product of the current and the resistance. And if that current flows from the plus to the minus end of a voltage, in order a voltage drop, then V is plus IR. If that current goes from minus to plus for the voltage, then V equals negative IR. Thanks for your attention. Please join us on the discussion forums, and I look forward to seeing you for the next lesson.